Good day, I'm Maile Matsiba. Welcome back to our channel. Today we continue with class test 4 of our CIR 123, which is the second chemical engineering module at the University of Pretoria. We are looking at part 2 of class test 4, and this is the 2011 version of class test 4. It says, first phosphorus pentachloride PCl5 dissociates at high temperature according to the chemical reaction equation. It says the following test was carried out in a constant volume reactor of 0.66 meters cubed. At T equals to 0, there was nothing in the reactor, and 5.42 kilograms of PCl5 gas was charged to the reactor at a temperature of 102.75 degrees Celsius. Now the question A says, what was, after the charge, the absolute pressure in kilopascals in the reactor? And we are given the atmospheric pressure there. So the question wants to know, immediately after they charged 5.42 kilograms of PCl5 at 102.75 degrees Celsius, what was the pressure then? What was the absolute pressure then? And just to put forth the the pressure equation is this is the equation to calculate the pressure, where N is the number of moles and R a constant, T the temperature, V the volume. So if we, according to this equation, we realize that if we're going to calculate the absolute pressure, we're going to need the number of moles. And it shouldn't be difficult because we have already been told that there's 5.42 kilograms of PCl5. So for us to be able to continue further in using this equation, we need to calculate the number of moles of PCl5 at those conditions. So we can just say the number of moles of PCl5, right, is equals to the mass of PCl5 over the molar mass is equals to the mass we know is 5.42 kilograms all over the molar mass of PCl5 according to the periodic table is 208.5 kilograms per kilomole. So if you use your calculator there, it gives you 0.025995 kilomole of PCl5. So this tells us that at immediately just after they charged 5.42 kilograms of PCl5 at that temperature, this were the number of moles. Now, if we have the number of moles, we can then calculate the absolute pressure of PCl5, absolute pressure of PCl5. Well, let me just also write here that after the charge, right, is equals to the number of moles is 0.025995 multiplied by R, we know it's 8.314, multiplied by our temperature. Now our temperature is actually 102.75 plus 273.15, just to convert it to Kelvin, all over our volume. We are told that it's actually 0.6. Now if you use your calculator, you can find that the absolute pressure PCl5 after the charge, I hope it's clearly visible, after the charge is equals to 135.4 kilopascals. So this is the absolute pressure of PCl5 just before it dissociates into PCl3 and Cl2. So this actually concludes our question A of part 2 of class test 4. So now we go to B. Now B says that the reactor was then slowly heated to 250.5 degrees Celsius and pressure rose to 29.2 psi gauge at T equals to T1. Now here we see that there's now T. Remember, initially it was just after the charge. Now at T equals to T1, which means it's some time afterwards. T1 is the time after the temperature has risen to 250.5 degrees Celsius and the pressure to 29.2 psi gauge. So the question is, what is the percentage dissociation of PCl5 at this time in those conditions? So percentage dissociation, just to briefly explain it, they just want to know, according to this reaction equation, to what extent, how much of PCl5 did decompose into PCl3 and Cl2. That's basically what the question is saying. And if we're going to be able to calculate that, we're going to first, the best way or the easier way that we can actually go about this thing is, remember, we know the number of moles just before it dissociates, right? So we can actually use the other conditions that we have to calculate the number of moles at this time at these conditions. And we use the comparison of the number of moles initially and the number of moles afterwards at T equals to T1 to find out the changes. So that is the approach we're going to use. So I've put together a few steps. So step one, right? We're going to calculate the number of moles of gases at T equals to T1. Calculate the number of moles of gases at T equals to T1. So while we're calculating at T equals to T1, it's not necessarily a specific gas. We just want to know the total number of moles, right, of the total number of moles at T equals to T1 after a certain portion of PCl5 has actually decomposed. And if we're going to do that, the number of moles equation we know is N is equals to PV all over RT, right? We have the volume, we have the pressure because we know the gauge pressure, and we are in A we're given the atmospheric pressure, and we also have the R, right, and the temperature. So it shouldn't really be that difficult, right? However, it's important that we're going to need to sort out the pressure first and make sure that we use it in firstly, we're going to need to find the absolute pressure, and then after we're going to need to convert the absolute pressure from PSI into kilopascals. So that is actually something we needed to do. So the first thing, let's calculate the pressure. Pressure absolute is equals to pressure gauge plus atmospheric pressure, right? So absolute pressure is equals to the gauge pressure plus the atmospheric pressure. The gauge pressure we are told to be that is 29.2 psi, right? Plus the atmospheric pressure we are told here that is 12.5 psi. So it's plus 12.5 psi, right? And if you use your calculator, it gives you 41.7 psi. So this is basically the absolute pressure. Now we need to convert the absolute pressure into kilopascals. We can just say, therefore, absolute pressure is equals to 41.7 psi, right, multiplied by the conversion factors 101.325 kilopascals all over 14.696 psi. So if you use your calculator, that gives you 283.51 kilopascals. So we know the pressure at these conditions is 287.51 kilopascals. And with that said, then we can go back to this equation and calculate the total number of moles, right, of all the gases combined at these conditions. So therefore, the number of moles, let me say at T equals to T1 is equals to our pressure, we know it to be 287.51 multiplied by our volume. It's a constant volume, so it's 0.6, right, all over our R, the constant is 8.314 multiplied by our temperature. Our temperature is 250.5 degrees Celsius. Now if you add 273.15 to convert it to Kelvin, it becomes 523.65. And if you use your calculator, it gives you 0.039 962 kilomole. Yeah. So we now know that at just after the charge, we know that just after the charge, before any PCl decomposed, these were the number of moles. And we know that at T equals to T1, which means at a certain time along the process where a certain portion of PCl5 decomposed, when the temperature was 250.5 and the gas pressure 29.2, these are the number of moles. Now we're going to use this to actually, and use our chemical engineering intuition to actually find out how much of PCl5 did decompose, because that's actually the key factor. If we're able to know how much of PCl5 decomposed, then we're going to know how much of PCl3 and Cl2 formed, because PCl3 and Cl2 formed depend on not on them on PCl5 that was formed, that was rather charged, but depend on the PCl5 that decomposed at T equals to T1. So now our important task now is to find out how much of PCl5 did decompose. So this takes us to our step 2. Let me write here that step 2, right? In step 2, we're going to say, we're going to define the number. Remember, we want to know the number of moles of PCl5 that decomposed. So we're going to define that at X. So we're going to say, let X be the number of moles of PCl5 that decomposed at T equals to T1, right? So that's basically we define X as the number of moles of PCl5 that decomposed at T equals to T1. So that is basically our approach. And if we can find that at X, if we can find that as X, then we won't be having a problem with finding PCl3 and also Cl2. So therefore, let me say right here that therefore at T equals to T1, right? PCl5 that remains is equals to, now I want to analyze the mixture. Remember, we have defined X as the number of moles of PCl5 that decomposed. So now the thing is, at T equals to T1, the PCl5 that remains is actually the total PCl5 that was there initially, right? So where's that? Yeah, this is the PCl5. Originally this was the PCl5, but we know that X amount of this PCl5 did decompose. So at T equals to T1, we know that total PCl5 is equals to this number minus X. So it's equals to 0.025995 kilomole minus X. X is what has decomposed, right? So, and then we also know that, going back to the chemical reaction equation, we can also check that, let me bring a new page just so that, yeah. So now from the, let me write here that from the reaction equation, if X moles of PCl5 decomposed, then X moles of PCl3 formed, and I'll explain it later, and X moles of Cl2, let me put gas here, Cl2 formed. This is the logic around this, right? Where's the reaction equation? Here. So we are basically saying that if we agree that is X amount of PCl5 did decompose, then we know that because the ratio of PCl5 and PCl3 is 1:1, then X amount of PCl3 formed, and also equally X amount of Cl2 formed. So we know that we've already calculated here that at T equals to T1, PCl5 is equal to the total minus the X that decomposed. And therefore, let me say, therefore at T equals to T1, now right, PCl3 is equal to X, right? And Cl2 is equal to X. So that is the point. So we know that at T equals to T1, PCl5 is the total that was charged minus the X, which is what was decomposed. And the PCl3, according to the chemical reaction equation here, is actually X, because this depends entirely on the PCl5 that decomposed. And equally, Cl2 also is actually X, because this also depends on the PCl5 that decomposed. And the ratios of these are 1:1. Therefore, we can say, therefore, at T equals to T1, right, total moles of gases is equal to 0.025995 kilomole minus X, right? So the total amount, now we are analyzing the total amount in terms of X. So the total amount of gases is the PCl5 that remains is here, plus the PCl3 that formed in terms of X, plus the Cl2 that formed in terms of X, right, is equals to 0.025995 kilomole, right? X plus X plus X, so it means 1x, 2x's cancels, and then you are left with X. So basically, this is the total amount of kilomole that is actually at this temperature, at T equals to T1, at these conditions. Let me bring that page. Here. So basically, at T equals to T1 at these conditions, in terms of X, this is the total amount of moles, right? And remember here that we did calculate the number of moles here. I hope that doesn't really confuse anybody. What we did here is we found the number of moles in terms of X. This is basically an equation. I can even name it one. We found the number of moles of gases in terms of X, right? But before we found the we know the total amount of, we know the number of moles in terms of X, right? And in terms of X, we know we know the composition of each one of PCl3 and PCl2, of PCl3 and Cl2 and PCl5 in terms of X, right? However, initially, remember, we did calculate the total number of moles, though we didn't have the details of how much was each one of the gases, but we knew using this equation that the total amount of moles is 0.03962, right? Now, with that said, we can basically, what we can do is we can go to our step 3. Right? In step 3, we calculate X, right? So if we're going to calculate X, we're going to need to understand that, like I just said here, we're going to need to equate this equation, this total number of moles, with this total number of moles. So we have total number of moles of two things. Initially, we have the first one we have the total number of moles without the details of which one is which. And then we also have the same thing, we have it in terms of X. So we're going to equate, let me say, so that it's easily understandable, equate equation 1 with the total number of moles, right, at T equals to T1, and solve for right? So that's basically what we're going to be doing. Because we know the number of moles and we also know the number of moles in terms of X, we can just say 0.025995 kilomole plus X is equals to this number here, which is 0.03962 kilomole, right? Therefore, if you actually solve, you'll find that X is equals to 0.03962 kilomole minus 0.025995 kilomole, right? So therefore, if you use your calculator, you'll find that X is actually equals to 0.013625 kilomole. So this is actually we now solve for X, and this X, like we said initially, this is actually the amount of this X here is the amount of PCl5 that decomposed, and equally it's also the amount of PCl3 gas that formed, and also the amount of moles of Cl2 gas that has formed. So we did solve that X, and this then concludes our step 3, and it takes us to our step 4. Step 4. Now in step 4, we're going to answer the question. The question says calculate the percentage decomposition. Now that we have all the information we need, we can simply then calculate the percentage dissociation. So calculate the percentage dissociation, right? And then we can just say percentage dissociation of PCl5, right? Let me mention here that of PCl5 gas, right? Yeah, the percentage dissociation of PCl5 gas is equals to the number of moles. Let me write it in words. Number of moles of PCl5 that dissociated, right, all over the number of moles all over the original number of moles of PCl5. And I don't have space for everything needs to be multiplied by 100%. I hope that's clearly, or should I rewrite it? Let me just try to write it properly. Sorry about that. Percentage dissociation of PCl5 gas is equals to the moles of PCl5 that dissociated, right, all over. Let me write the initial number of moles of PCl5, everything multiplied by 100%. And let me do this here. I'm going to need another page. If we're going to rewrite that here, remember we have the percentage dissociation is the number of moles of PCl5 that dissociated, and this is actually the number. Therefore, percentage dissociation is equals to 0.013625 625 kilomole all over the initial amount of kilomole, which was 0.025995 kilomole multiplied by 100%, and if you use your calculator, it will give you 52.4%. So the answer for question B, which says calculate the what is the percentage dissociation of PCl5 at t equals to 2:1 is 52.4%. So this then wraps up question. It wraps up question B. Yeah, it wraps up question B. Then this takes us to question C. In question C, it says, what is the partial pressure of PCl5 in the reactor? Now, the equation for pressure is P is equals to nRT all over V. Now, we all know that, pressure depends on the number of moles. So the question is, remember, so this question is basically saying, what is an amount of pressure that is caused by the PCl5 in the reactor at t equal to T1? So after a certain amount of PCl5 has decomposed, so what is the pressure only based on the PCl5 that is present at t equals to T1? So if we want to know that partial pressure, we can actually get the number of moles of PCl5 at that temperature or at that time, and then we can use the equation to get that. And I've put together some short steps. So step 1, we say calculate the number of moles of PCl5 at t equals to T1. So we say calculate the number of moles. Calculate the number of moles of PCl5 at t equals to T1, right? So we can just say number of moles of PCl5 at t equals to T1 is equals to the original or the initial number of moles, 0.25995 kilomole, minus the number of moles that decomposed is 0.013625 kilomole, and if you use your calculator, it gives you 0.0123 kilomole, right? 0.0123 kilomole. So this is actually the number of moles of PCl5 at t equals to T1. And because we have it, then we can just say pressure of PCl5, which is the pressure as a result of PCl5, right? The partial pressure is equals to the number of moles is 0.0123, right? 7 isn't, and then multiply by R, 8.314 multiplied by the temperature, and the temperature we know that it's 523.5 because it's 250.5 plus 273.15, and then all over the volume. So it's a constant volume reactor, so it's still 0.6, and if you use your calculator, it gives you 89. It's 89. Sorry, my hand is tired, that's why I can't write properly. Sorry about that. So it's 89.7573 kilopascals. This is the partial pressure of PCl5, or you can say it's actually the pressure as a result, the pressure in the 0.6 meter cubed reactor as a result of PCl5 at t equals to T1. So this also wraps part C, or question C of the equation. So now we go to D, which is the last question. And D says that what is the density in kilograms per meter cubed of the gas mixture? So this shouldn't be difficult. So remember, we have density is equals to mass all over volume, right? So density is equals to mass over volume, and is equals to, we know the mass. Initially we were told that there's actually 5.48 kilograms. So at T equals to T1, the mass does not change. Even if there would be a reaction there or whatever that happens there, the mass does not change because it's a closed system, it's a closed reactor, and so whatever that happens, only the moles and the pressure will change, right? But the mass does not change. So if we want the density, we can always go back to the amount of mass that was charged there initially, which is 5.42 kilograms. So we'll say 5.42 kilograms all over. The volume is also a constant volume, so it's 0.6 kilogram, 0.6 meters cubed, right? Yeah, and then if you use your calculator, it gives you 9.033 kilograms per meter cubed. So this is actually the density of the gas mixture, the density of everything, or the gas mixture at T equals to T1. So thank you for your time. This wraps up part 2 of class test 4, and it wraps up class test 4. So thank you for your time, and I hope we meet again in our next video.